this is where the really fun stuff happens, because this is a kind of a complicated region to integrate over. We're going to have to do a little bit of hand waving here, but don't worry, we're going to get through it. This domain of integration is supposed to be enclosed by the planes z equals 0 and z equals x plus y plus 5. This is a tilty plane on the top, right? It's one that slopes both in x and in y. So it's not even just one of those things that's like a line in one of the planes, you know, beamed in both directions. Nope, that's not sufficient for this. But because we know this is cylindrical coordinates, let's actually look at not that condition first, but these ones first, because this is going to allow us to describe the domain pretty easily. And then it's actually going to become clearer what the tilty plane does to this domain. So x squared plus y squared equals 4 and x squared plus y squared equals 9. You should recognize these as the equations of a circle with radius of 2 and a circle with a radius of 3. Of course, in 3 dimensions, a circle gets beamed all along the axis that's not in its equation, and so it becomes a cylinder. So it's bounded by those cylinders. Well, if it's bounded by a smaller cylinder and then a larger cylinder, what it must be doing is filling up the space between the cylinders. So this is like, it's kind of like a thick-walled cylinder of glass or something like that, where the glass, the portion that actually forms the thickness of the glass, that's what we're looking at. So it's going to be something like this. We're going to have 1, 2, 3, 1, 2, 3. We're going to have those 2 circles. And yes, they are going to get completed as they go around. And then you beam them up. And voila, we have it. This is our hollowed out cylinder. It's like it starts solid and then you drill something with a radius of 2 through the center. Well, think about what it would mean to pass a plane through this. Here's what it would mean. Think of this sort of shape. If I cut this, and by cut, I mean at an angle like that, not level, but at an angle like that, because it's going to tilt, right? We know that this is a tilty plane. Now, don't make the rookie mistake of drawing it like this, okay? This, and no, that's not really a pretty way of doing it. When you cut something that's curved and you cut it in a straight line, then the cut actually ends up itself being curved. Now, you should know that. This is almost like forming a conic section. Think about cutting a cylinder at an angle, and you'll be able to see the shape you'll form will be an ellipse. Well, just be, you know, convincing with your picture and show that the cut is a curved line. So I don't really want to engage with how exactly the cut is going to look, but what I know is that 1, 2, 3, 4, 5, that's going to be the z-intercept of this plane. And let's see, it'll tilt backwards because as x goes more positive, it will become more positive. As y gets more positive, it'll be more positive. So it's going to slope like this sort of way. But it's so hard to draw this and difficult to conceptualize too. It's much easier to simply write the bounds for the domain of integration. So z, we don't have to worry about what it looks like. We just need to know that z is going from 0 up until x plus y plus 5. The bounds take care of all that complicated stuff for us. Now we're doing this in cylindrical. If we do it in cylindrical, we need to make sure that we're picking the other variables to be r and theta, not x and y. R, in this case, does not start at 0 because we're only looking at the interior of this ring. So r goes from 2 up until 3. See how that happens? Now, what about theta? Well, there's a possible kink here where maybe theta doesn't do its usual 0 to 2 pi thing. The only thing that would make that happen is if the intercept of the plane, when it hits the xy plane, is going to like cut off before you get a chance to reach the end of the circle. So like if you had a plane that intercepted like right there, then that would be a problem here. But it's not too difficult to see that that's not going to happen, because think about what you would need in order for z to be 0. You'd be looking at points like -2, -3. And that is going to be outside of this circle. So you're not going to have any problems with the plane slicing it off before theta gets its chance to go from 0 to 2 pi. Okay? Okay. So now that we've got the bounds, we can write the integral. X here, when we convert to cylindrical, it's essentially the same as writing it in polar. So x is going to be r cosine theta, and then the integral will be, let me see, integral theta from 0 to 2 pi, r from 2 to 3, and z from 0 to x plus y plus 5, r cosine theta, r dr. Well, I'm going to switch the order of the differentials because I'm doing z first. So dz, and then dr, and then d theta. Well, this is correct. There's nothing wrong with it, but usually we wouldn't write the r here. We just fold it into that. So let's do that. We'll just square that instead. Okay. With the way that we've written these bounds, it makes the most sense to do the z first. So let's do that. The inner from 0 to x plus y plus 5 of r squared cosine theta dz. There are no z's here. So this is going to be r squared z cosine theta. And we forgot something, didn't we? And you probably were noticing this. Looky here. Now, I make these mistakes, because they're mistakes, but it's good for you to see, how do you see a mistake? How do you fix it? Well, this x and y thing, that's not a good bound of integration when it comes to doing cylindrical integration. So this is sort of like, sad. We don't want that. But how can we make it happy? We can make it into a bound that does make sense for cylindrical. Well, z then would go, not that, but it would go from 0 up until r cosine theta plus r sine theta plus 5. See how the x and the y turned into their polar or cylindrical versions? There you go. So now we're nice and happy. So let me go back and fix that. That's now integrated from z equals 0 to z equals r cosine theta plus r sine theta plus 5. And this right here is just going to get replaced with that. Okay, so r squared z cosine theta, we're back on track. And this is going to get evaluated at z equals 0 and z equals r cos theta plus r sine theta plus 5. This might be a little messy. R squared cosine theta, that's this part. And then we're going to multiply that by r cos theta plus r sine theta plus 5. Multiply through. R cubed cosine squared theta plus r cubed sine theta cosine theta plus 5r squared cosine theta. Which variable is next? Ah, it's r. Okay, so the middle, that goes from 0, oops, not 0. It goes from 2 to 3. R cubed cosine squared theta plus r cubed sine theta cosine theta plus 5r squared cosine theta, and this is with respect to r. Okay, this isn't bad. We're saving a lot of the difficulty for the theta at the end with all these powers of trig functions and all that jazz. So we integrate this with respect to r. The first term is going to be r to the 4th cosine squared theta over 4. And then another r to the 4th over 4, but this time with sine theta cosine theta. And finally, a 5r cubed cosine theta over 3. This gets evaluated at 2 and 3. There's no 0 to save us here, which is like super annoying. But, you know, sometimes you don't get to play the game you want. You get to play the game that is dealt to you. So put in the 3. That'll be, in the first case, 81 cosine squared theta over 4 plus another 81 sine theta cosine theta, again, over 4, plus 5 times r cubed. R cubed is 27. 5 times 27 is half of 270, which is 135. And over 3 reduces to 45 cosine theta. So that's the 3 version. Now we have to subtract the 2 version. 2 to the 4th is 16. Divide by 4 is 4. 4 cosine squared theta. 2 to the 4th again is 16. Divided by 4 is 4. So then this is plus 4 sine theta cosine theta. And then plus 5 times 2 cubed is 8. So 5 times 8 is 40. That's 40 cosine theta over 3. Some common denominators would be nice. Let's see, one at a time here. I'm going to need this to have a denominator of 4. So that's going to be 16. So we have 81 minus 16. That's going to be 65. 65 cosine squared theta over 4. So now we've done those. And then we're going to have 81 over 4 minus 16 over 4 again. So this will be the same, 65 sine theta cosine theta over 4. And then plus put in, oh, whoops. Sorry, I forgot what we were doing. 45 minus the 40. So with these having common denominators, kick the 45 back up to the 135 that it was originally. That becomes 135 minus 40, or 95. Cosine theta over 3. Okay, so now we've done this and this. The only thing left to do is theta, and it's going to be sad because we have all these trig functions. Remember, though, you can use trig identities to simplify these integrals. So we're going to use, in particular, the cosine double angle identity. We'll also be able to use a nice treat. We'll be able to use the sine double angle identity as well. Remember, cosine of 2 theta is cosine squared theta minus sine squared theta. And if we want to isolate this, it's going to turn into, well, you replace the sine squared with 1 minus cosine squared. And this becomes 2 cosine squared theta minus 1 So then isolating cosine squared, you get cosine squared theta equals 1 plus cosine 2 theta all over 2. So that's going to be what we can swap in there. All right. Now, what about this sine theta cosine theta business? Don't start thinking u substitution, because it's just not necessary here. But you should be able to apply a trig identity to do this. It's pretty easy. Remember, sine of 2 theta. When you want to simplify powers of trig functions, you usually use the double angle for cosine. But this is a case where you need to know sine of 2 theta. That's 2 sine theta cosine theta. So what if we take 1/2 of each of those? Well, now it's simply sine theta cosine theta. So the sine theta cosine theta factor here, that's going to be replaceable with 1/2 sine of 2 theta. And the cosine squared thing is going to be replaceable with that. So just rewriting this before we do the final integration, it'll be 65 over 8, making this 4, talk with this 2. 65 over 8 times 1, and then plus cosine 2 theta. So 65 over 8 plus 65 over 8 cosine of 2 theta. And then this is 65 sine 2 theta over 4 over 2, which is over 8 again. And this one doesn't need to be changed at all. All right, so now we want to integrate this from 0 to 2 pi along theta. 1 by 1, 65 theta over 8 plus integral of cosine is sine. And because of the 2 theta, let's see, if it were 65 over 8 sine of 2 theta, now when you take a derivative, you'd end up multiplying by 2, causing the 8 to become a 4. We don't want that. So what we need is another 2 down the bottom to make it a 16. Okay? The same deal is going to happen with the sine 2 theta in the next term. So let's just do that. That's going to be 65 sine 2 theta over 16. Oh, well, no, I have to actually take an integral. The integral of sine is negative cosine. So this is going to be minus 65 cosine 2 theta all over 16. And then this integral of cosine is sine. So this will be plus 95 sine theta over 3. And this is as theta goes from 0 up to 2 pi. Hopefully we'll have a lot of zeros here. That would be nice. 65 times 2 pi over 8. Plus 65 over 16 times sine of 4 theta. Sine of 4 theta, or sine of 4 pi rather, is 0. So this is just a 0 term. Then minus 65 over 16 times cosine of 2 theta. Well, this is cosine of 4 pi. And remember your unit circle, 4 pi is right here, and the cosine of that is 1. So this will be minus 65 over 16 plus 95 sine theta over 3. When we put 2 pi in for that, that's 0 as well. So that's the first evaluation. Now we have to subtract the second one. Put in 0 for theta. The first term is a 0. Plus sine of 0 is 0 again. Minus 65 cosine of 0 over 16. Well, cosine of 0 is 1. So this is minus 65 over 16. Boom. And then plus 95 sine of 0 over 3. That is yet another 0. So what you get here is this. 65 over 16, that's negative, minus negative 65 over 16. So those end up canceling out. And the only thing that's left is this term right here, the 65 times 2 pi over 8. The 2 and the 8 can reduce. That becomes a 1 on the top and a 4 on the bottom, or 65 pi over 4. Phew! If you made it to the end of this, then you are a real trooper. But that's the value of the integral.